about memory. This is just about how to deal, first of all, with the distributed memory nature of the host and the coprocessor, and then at least some insight into memory-based tuning. I cannot tell you anything about it, but at least I can tell you a couple of best practices that when you apply that to your code, it will also pay off on the Xeon part. Okay, we need to talk about the basics, of course. I will again go over the explicit offload and the implicit offload model and tell you some more specific things. And then we will talk about performance tuning, which is also kind of related to this memory topic. So let's dive right into it. During the coffee break, we've been already asked what's the memory hierarchy, and the only thing that we can say is L1 and L2 cache and the GDDR5 memory. The sizes that you see on the system today is just a snapshot. They may change any time, but it's certain that we will have L1 and L2 cache. Okay, that's pretty much fixed. And we have a standard Linux system on it. And this Linux typically today supports 4K pages and 2 megabyte pages. And I will show you how you can utilize those larger pages because they have certain performance implications. There are drawbacks to using them, but there are also benefits. And it depends on your application, your memory access behavior, if this actually pays off. But the support is there, and you can basically utilize them. Okay, explicit offloading. You've already seen that picture. It's just to make you again aware of what happens when you do the offloading. So first, we allocate a bunch of data. We copy over the data from the host that we need to compute, do something with it. So we read or modify it. Then we copy it back, and afterwards we release it. Okay, and we do a bitwise copy. So that's basically something like a mem copy through DMA. There is no pointer translation. Let me again iterate on that. You cannot transfer a pointer type between the host and the mic and back. Okay, that doesn't work. Okay, so the first optimization that you can do is you can obviously leave data on the card, and you can force the system by specifying a number for the card in the target clause to specifically always hit the same mic device or Xeon Phi device in your system. Okay? If you don't specify anything, the runtime system basically picks whatever it likes. Okay? It could be round robin, it could be randomized, it could be load based, whatever. But there's no guarantee that you would always hit the same device if you have, of course, more than one device. Okay? If there's only one, there are good chances that you always hit the same device. Okay, so it is technically it can be an idea to specify the device, or if you want to actually utilize more than one device at the same time, you could also have a for loop that iterates over the devices and accesses a device of your choice. Okay, we already heard about this in, out, and in-out clauses. There needs to be a break in there because otherwise it's not obvious. So this is the way for you to control the direction of data transfers. The default, most of the time, is in-out. So the compiler transfers something to the card, lets it process there, and then copies back. So we had this Hello World example, and one of the questions at the end was, where does those 8 bytes transfer come from? And if you recall the code, we had this numthread clause or numthread variable where I computed the number of threads on the mic device. Okay? And the compiler transferred an empty value of that variable to the device. We overwritten the code overwrites the uninitialized value and copies back something meaningful. Okay, and one optimization, since you at least want to read the value on the host, is to have an out clause specifying for num threads to avoid the initial data transferred to the mic. Okay, so I don't care about 8 bytes, but it could be a 2 gigabyte data structure. Okay, so make sure that you don't copy anything that you actually don't need on the mic. Or you can have no copy to indicate to the compiler that something shouldn't be copied because it's already present or it's allocated there. And you can, today, as of today, you can have static or global variables in a no-copy clause. So you can have a global array, like we did in this red-black Gauss-Seidel application. And you can basically say no copy for this, and it will remain on the mic only, and no transfer will happen. And later, well, it should actually be on the machine right now. So beta 2, update 2 is 060 compiler. So you can now also have a scalar on the stack that is persistent on the mic. Of course, the lifetime of this stack variable is limited to the current function's call stack. Okay, so you cannot have this scalar persisting several function calls. And probably later we might see something like arrays that you can allocate on the stack and keep persistent across different offload regions in the same function. Okay. And yeah, the way to control this is alloc if and free if. I already talked about that a bit earlier. So whenever there's a true in the alloc if, it means transfer and allocate, but keep. And free if the condition evaluates to true, means free and destroy. Okay, transfer back and destroy afterwards. So basically, what you always need is kind of an anchor point where you can hook up your data structure to. And typically, you do something like a global struct with all the pointers so that they are at least kept together in a single logical data structure. You allocate something. And then you can use this data structure to pass the same pointer between functions. Okay, from a software engineering perspective, this is horrible. I know, but the only thing, at least in C, to make something really global is to have a global variable. Okay, or you need to, move the pointer between all those function invocations back and forth, which is also a bit annoying. Okay, but that's the way it works. And you can also, if you flag that with an attribute target mic, you can replicate that anchor point on the mic as well and hook your data structure into those global variables. Okay? Okay. And, well, what you do then is you allocate this cache structure, you initialize the data on your host, and then, and this is, can I get, so here there's a length somewhere, okay, which is totally hidden by this nice bullet point. Okay, so we say target mic, copy the A data into the mic, free if 0. So that means copy it over and keep it there. Okay? And then at the end, oh, it's 128. Ah, nice. And so on the other end, what you can do is you can say no copy. Okay, it's already there. Don't copy it again. Don't fiddle around with allocation. Just keep it on. It's already on the device. Do nothing about it. Okay, and then you can just work on it. But still, you need this hookup where you basically can get the global pointer, the same global pointer back across different function invocations or different threads or whatever. Okay, that's very, very important. Okay, so the compiler somehow takes care that it references the right A here. Okay, and I think I think I put up an lab exercise that actually did that. So one of the optimization steps in lab exercise 3 was to have those no copy and alloc if and free if clauses to play around with that. Okay, you've seen that picture again already. You see it again. So important, we got the host memory, we got the KNC memory, we got some same address range, and the data is copied, conceptually copied back and forth between so-called synchronization point, and those synchronization points are obviously before the offload starts and after the offload starts. Okay, so any data that the KNC touches between those two synchronization points shouldn't be touched on the host. Okay, same as with threads. If two threads see the same shared variable, don't touch them at the same time. Okay, that's easy to understand. Otherwise, you've got a race condition. And if you need to hunt them, you get gray hair, as I did. Okay, but the good news is sometimes we have very complex data structures, linked lists, trees, whatever, arbitrary object graphs. And so with that, we can share that. And we don't need marshalling or serialization or whatever you may call it. Yeah? Yeah. Oh, yes, this is a minor but an important point. You cannot propagate exceptions between system boundaries. That doesn't work. So when that happens, you need to have some, I don't know, flag variable to indicate that there has been an exception. Okay? Because the call stack from the mic doesn't make sense on the host. Okay, this is just a very simple example, which makes me actually hungry. So we have this little donut here. We want to compute the area or the surface area, at least if it's a 2D donut. So we have the inner circle, we have an outer circle, and basically what we do is we do a Monte Carlo simulation. We drop little needles on the poor donut and count all those that fall inside this area we described by those two circles. And we implement that with the offload model. Okay? So how do we do that? So first of all, we want to offload something, and this is Silk shared. So we flag the FindArea thing here as Silk shared. Then for each function instance, we have a set of private variables. And then we do a parallel for on the number of measurement instances that we want to evaluate. For each instance, we do rand_r, so we provide a random number. And rand_r is thread safe. It's the re-entrant version of it. Then we do some mathematical fiddling that I don't quite understand. But anyhow, if that holds true, we count the needle as inside the donut. Okay, that's a very scientific example, I believe. And then, you know, the area is 4 times that, blah, 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 and so forth. Okay? The important thing here is this inside is a so-called Silk hyperobject. Okay? Because what you want to do is this loop runs in parallel across different threads, and you got this little sum variable that should count all the needles that are on top of this donut. Okay? What I said, better say sugar crystals. It's more realistic example. And so the typical approach, for example, in OpenMP is to put up a reduction and have local partial reduction variables where each thread sums up a local sum, and then at the end we do a global reduction. Okay? And in Silk, since we don't have clauses or pragmas or anything, all this is hidden inside such a Silk hyperobject. Okay? So basically a Silk hyperobject is a data structure where you can reduce values in, and Silk somehow takes care that there are no race conditions and multi-threading issues on a single hyperobject. Pretty nifty stuff, and one of the cool things in Silk. Okay, you guys can try it out tomorrow if you want, if it vectorizes or not. Okay, and then on the host, so that's the main function that we execute on the host. What we basically do is we Silk spawn a Silk offload. Okay, so this basically runs on area with radius R2. So that's probably the outer diameter of our donut. Okay, so we count all the sugar crystals that fall into the donut with not respecting that there's a little hole inside. Okay, and then we do the same in a second thread for the inner circle. Okay, and so basically we count the sugar crystals on the whole circle and count those in the inner circle, and we subtract those two, and we got the area of the donut. Okay, sounds reasonable? Okay, so this and this runs asynchronously, and we put up a Silk sync to make sure that this Silk task has been completed before we reach this code down here, And then, you know, well, we count the sugar crystals, some pi computation, some other computation, and then it says, well, donut area is X. Okay, that's the way you can do it in the implicit offload model. And, you know, this, all that, what happens here is automatically transfers back and forth between the mic and the host. Okay? Okay, now the other thing is, yep. In Fortran, you would do the, first of all, the directive-based offloading. And I will have an example in about 3 slides how you could do this, roughly the same in Fortran. And I will point you to that in a minute. Okay, overlapping communication and computation. We already had a question. I think you asked the question. How much overhead it is in the coprocessor to transfer the data. And so there's a certain overhead to that. I don't know how much it is, but you're limited basically by PCI Express bandwidth and communication latency to set up a remote data transfer, to actually copy the data, to tear down the transfer and that stuff. Okay, so it's always a good thing to keep the mic running while we transfer data from the host to the mic. And probably we can also transfer data that we already computed on the mic back to the host. Okay, so if we can do that, we maximally utilize the system's resources. And that's the idea of double buffering, triple buffering, whatever strategies, also in MPI, for example. Okay, so this is the idea. We have on the host a data block. We transfer that to the target. And as soon as we starting processing, we start to transfer the next data block. Okay, and hopefully when that guy is finished, we can take on this guy and also transfer the next data block and utilize the PCI Express bandwidth while the coprocessor is working on something else. Okay, so this is what we want to do, and this is now closely related to alloc if, free if, and asynchronous computation. Okay, so to set up everything, okay, we need to set up a couple of things. So first of all, we have a special pragma to not do an empty offload statement to transfer data. So this is basically, you can view that as a pragma offload, all the clauses, and then a set of empty curly braces with an empty statement block. And this is more readable. Okay? So we do this offload transfer to the mic, and now we need to attach the number of the mic because we want to keep the data specifically on a very specific device, and in the runtime system may not fiddle around with the allocation of offloaded code to devices anymore. Okay, so everything goes to the first mic. We copy in the count variable. That's probably the number of iterations we want to make. And we don't copy in actual data, but we allocate it. Okay, so all we do is we allocate our in buffer, the result buffer, version number 1, and version number 2 with a certain length, and we just allocate, but we don't free it. Okay, if you go back, we need 2 buffers. We need one for the data that is currently in flight, and the second buffer stores the data we are just working on. Okay, double buffering. Okay, so we allocate those buffers on the mic. We do something, and then at the end, we again don't copy anything back and forth. We just tell the compiler, free the data structures that we allocated here. Okay? That's the reason for alloc if and free if. Okay, now for the real double buffering. So in every even iteration of our algorithm, we do the following. Before we start, we transfer the first buffer. So there's a special case. The first buffer needs a special handling, but then we can trigger this even odd algorithm. So the first offload just transfers the first buffer into the system. So we don't need to allocate anything. We don't need to free anything, because in1 has already been allocated on the mic. Okay? We just need to copy data from the host into a pre-existing buffer. Okay? Now, in every even iteration, what we do is we do basically the same, but now we copy to buffer 2. Okay? Same again. It has a certain length, and we don't need to allocate, and we don't need to deallocate because it's already existing on the mic. The space for the data is already being created. Then we do a pragma offload target mic, no copy, because the data is already there, and we compute on the first buffer. Okay? And now we need to synchronize. Now we need to make sure that the data that we are currently sending is already there when we need it. Okay? And this is where signal and wait comes into play. Okay? So when we transfer the second data chunk, we put up a signal on the pointer to it. So whenever this offload pragma is complete, it will fire up a signal and tell somebody, hey, I'm done. Okay? At the same time, this code fragment here may only run when the first buffer has been transferred. And that's why we put up a wait on the first pointer, on the first buffer. Okay? Now, second slide. In every odd iteration, we basically do the same, but now roles are switched. Okay? So we move everything into the first buffer. Again, no allocation, no deallocation. The buffer is already there. And we signal on in 1. Remember the blue part on the previous slide waited on in 1? And now we are signaling, telling the other offload, hey, your data is ready, go. Okay? And here's the same basically for to compute on the second buffer. So we don't copy the in2 because it's already there, and we wait on in2. Okay? So whenever this offload is completed, it will signal on that signal slot, and this guy will start executing. Okay? That's the basic idea of asynchronous offload. And in your example with the donut, you would put up a signal on X for the first offload and compute the second on the host, okay, the second FindArea. And then instead of the silk spawn, you would put up a pragma offload wait on the signal slot you did for the first offload, the first FindArea call. Okay? Yeah, oh yeah, and we of course sometimes later we need to copy out the result data. Okay? You can make that a little more complicated to also stream result data, but I think you get the basic idea behind it. Okay, pages, large pages. The problem with 4K pages basically is there are just a lot of them. And you frequently get page faults when you walk the memory because you allocate data in basically 4K chunks. And so for every new 4K that you touch, you get a page fault. And they are really expensive. It's a couple of 10,000 cycles that we need to spend to process them. So what basically happens is you get a segmentation fault in your code. The operating system is triggered. It looks at your code and says, oh yes, I know this page. Let's get it from somewhere. Put it into the probably take it from disk. Update the TLB, and then relaunch this memory access that caused the fault. So this takes a lot of time. Okay? Now if you take 2 megabyte pages, you can imagine that you get a lot less of those page faults. Okay? But nothing is for free. The sum of all pain is equal. So for 4K pages, you cannot cover a whole big data set of a few gigabytes without frequent page faults. You don't get as many with 2 megabyte pages. But the downside is that allocating those 2 megabyte pages and mapping them actually is a really complicated effort for the operating system. Okay, so you don't get as many page faults, but allocation is much more complicated for the operating system. And now this is, kind of a trade-off. If the data in the main memory isn't allocated that often, you could probably take 2 megabyte pages and pay the penalty when you allocate the data. Okay, so this is, playing around with your application and seeing what's best for Mike. And this also applies to Xeon, because Xeon also is capable of those 2 megabyte pages. And so you really need to make a measurement if 2 megabyte pages actually pay off. Okay, and of course the DMA engine basically works also on pages. And so you need to set up the DMA for 4 kilobytes and then tear it down, and so you can imagine that the bandwidth or the latency gets better when you consider larger pages. Okay. How to use it? Well, basically, if you use the implicit offload model, you can use libhugeTLBFS, which is kind of a strange name for something that controls the page allocation strategy, but it's implemented as a file system in Linux. Why not? And so you can basically tell the compiler to use it, or the runtime system to use it by setting this this variable to the right value. Yeah. Okay, and in the explicit model, when you're working natively, you can use malloc and standard memory mapping techniques to tell the operating system to place your data into 2 megabyte pages when you touch it. Okay, so the reason why you can split it up is when malloc starts and actually allocates memory, it just returns a pointer, but the data hasn't been allocated. So you can try that on your Xeon if you want. You can do a whole set of mallocs for, I don't know, until the virtual address space is exhausted, but when you start touching the data, you're in trouble. Okay, so malloc just returns a pointer and a promise that it will allocate the pages when you need them, but it doesn't actually touch them. And so what you do is you malloc and then mmap and then touch the data, and then you get 2 megabyte pages. That's the idea behind all that. And you can do that either in the native mode or the offload mode. Okay, because in the offload mode you got full control over what's going on. Okay, what else? So there are several differences between mmap and hugeTLBFS. I would rather call hugeTLBFS more abstract, and it gives you more control over also placing different code segments and data segments of your application automatically into 2 megabyte pages. So since you don't control the allocation of the data segment, BSS, that's everything that is initialized statically with zeros, and the text segment, which is your program code. Since hugeTLBFS basically works before your application starts already, it can control these. With memory map, you can just allocate that into 2 megabyte pages, what you're allocating in your code already. So when the application is already running. Okay, and yeah, and there's a certain difference between what actually goes into 2 megabyte pages. When you turn on hugeTLBFS, everything goes into 2 megabyte pages. There's no way to select that. Okay? If you want to be selective about this data structure, please 4K, this data structure 2 megabyte pages, you need to do the first one with memory mapping. Okay? But it's really easy to do that. So the first step is you need to tell the operating system how many 2 megabyte pages it should reserve for applications. So in this case, let's say we are satisfied with 128, and you echo that value into a certain prox file system pseudofile, and the operating system will adjust internal data structures to have 128 2 megabyte pages available for each application. But beware, those pages are gone. They are no longer available for other applications. Okay, so be sure that you don't exhaust the memory of other applications unnecessarily. Okay, and then the only thing that you need to do is you need to allocate something, and then since this just gives you a size of 120 megabytes, you mmap that. It's an anonymous map. It's private. You know, some memory map stuff. And here you say map hugeTLB, and the operating system takes care that P now points to an address space that is in this 2 megabyte page arena. Okay, that's all you need to do. But it's expensive. This call, runtime call, is very, very expensive. But at the end, it pays off since you get less TLB misses. Okay. How does it work with libhuge TLBFS? That's also easy. Get the file or get the download, compile it yourself for Mike. Then also echo into this number of huge pages file again the number of 2 megabyte caches that you want. And then basically you mount this virtual file system for the large TLB pages. And what you need to say is huge TLB more cores equals yes. The library path should point to where libhuge TLBFS, that's a complicated name and lots of acronyms, is located. And then you do a LD preload, and the library automatically takes care of overriding all the malloc and all the frees, news and deletes, whatnot, and other allocations in your code to make sure that they all go into those 2 megabyte pages. Okay? No program change, no compiler, no recompilation, nothing. It's just based on overriding a couple of weak symbols in your application. Okay, that's basically it. If you also want all your segments to go into 2 megabyte pages, it's a little bit more of effort because you now need to change the linker script so that the linker, basically moves everything to the right spot. Okay, and if you ever want to know if there's some memory left, you can put up a certain number and see how much you actually use by looking into this meminfo proc file system thing and grabbing for huge pages 3, and it will tell you how much of those pages you actually used and how much are free. Okay? If you need more of them, your application will die. If you need less of the huge pages that you allocated, you basically steal memory from other applications and other processes. Okay, so you should definitely know about the data size that you need to tune it as much as possible to not exhaust the memory. Okay, I said that already. Yeah, and if you do that in offload mode, it's basically the same. Now you need to say the mikenv prefix is mike underscore. I should remove the underscore probably because that's an issue. Then you say, well, I want to use huge TLBFS. Please preload it, and then the only thing that you need to do is malloc. That's it. Okay, and again, this library will take care of moving everything here into 2 megabyte pages. Okay, data locality. This is something. This is especially true on Xeon platforms, and it's also true for Mike because they are kind of on the same scale of properties. It's different to GPUs. So whenever in GPUs your memory bandwidth is kind of on the limit, you just throw more threads into the problem. Okay, that's why graphic cards usually take on millions of threads, because the threads are used to hide latencies of the main memory. Okay, we cannot do that in the mic. So, well, you can start 1 million threads, but it's probably not that beneficial. Okay, so the usual thing that you do on Xeon, if you've got a bandwidth problem, you take the same number of threads, but you do something like cache blocking. Okay, so you write your application in a way that it best utilizes the caches, uses temporal locality, spatial locality, and whatnot to work as much as possible out of the caches. And this is what I want to show as an example. So this is a 7-point stencil from some code from Tokyo. It does something very, very complicated. It's, I don't know, probably it's a PDE solver or something. And typically those codes are bad in terms of cache behavior. Okay, but on the same end, you can rearrange those loops so that they make better use out of the cache. And this is how we do it. So when you when you consider a certain stencil invocation during execution, and let's say we keep z fixed for a while, then we need y equals 5 to 7. Okay? If we go to the next set, we're going to use the same y's again. Okay, so we can exploit that structure. X is non-critical because X is, along the cache lines already. Okay, so if we can rearrange the loops in a way that we only increment the set when we already have y in the cache, we can reuse those values from the previously loaded cache values in the cache. Okay, that's the basic idea behind that. And this is how it was done in the code. You can it's also in the lab material, so you can have a look yourself. So the key idea is you define a y blocking factor so that we don't exceed the cache size. We also rearrange the loops a bit, and so the outer loops now runs in a certain block size, in a certain stride, so that the data just fits into the cache. And then we have an inner loop that basically runs through whatever is currently in the cache. This is kind of the same idea that Hans was presenting earlier, where we introduced this fake vectors of a small length. This is basically exactly the same idea. Okay, Hans did it to make use of the vector registers, and I'm doing it to make use of the cache lines. Okay, basically the same idea. And of course, you should use the collapse clause, and whenever there's a compiler that doesn't support it, complain about it. It's in the OpenMP specification since 3 years, and there are a few compilers that really have problems with very, very simple loops to compile that correctly. Okay, okay. Then it seems that in this particular case, it's already good enough to have 3 threads per core. So my little Hello World program launched 4 threads per core, and we've seen a couple of cases where the code is already saturating the memory bandwidth and the cores in a way that you just need to put up 3 threads to get the best performance. Sometimes it's 2 threads, sometimes it's 3 threads, sometimes it's 4 threads. Okay, so this is also something that you need to play around with. Then, of course, affinity. In this case, scatter is the best result because you try to avoid clashes on the same cache to get maximum cache per thread, so to say. Okay, and if you want, you can walk through this lab tomorrow in the free time to see how that works out and how the VTune profile looks and everything. Okay, alignment. Alignment is important. So whenever you do vectorization, you get the most performance if the data is aligned to vector boundaries. That means in AVX, this is 32 bytes, right? Is it 32 bytes? Yep, 32 bytes. So you should have a 32-byte alignment. Then the load instruction for the data is as fast as possible. If the data is a little off, you can imagine what happens. We need to get the first half of the vector or the first part of the vector shifted accordingly so that it fits the machine register, and then do a second load to get the rest from a little above the data we just loaded. Okay? On K and C, if you look into the architecture specification, it's even worse because we need to execute 2 instructions. The first one does, load the lower half, and the other one loads the upper part. And even worse, there needs to be a jump instruction in between because of the instruction semantics. Okay, that's the way it is. It's complicated and it costs performance. So alignment is key. Yeah. So better make sure that all your data is always aligned. Use the right versions of malloc and make sure that everything that you allocate in your application is always aligned. Okay? It's not possible, it all means. So if you consider a 2-dimensional data structure or a 3-dimensional data structure, you can only align 1 dimension. The other one will always be out of sync. Okay? unless you choose a data size that is a multiple of the vector length, which of course you cannot do if your problem size is 15. Okay, then you're in trouble. Okay, the first thing that you need to know is the L1 and L2 cache have a certain size. Those sizes that are on the slide is just a snapshot as you have them in the systems today. Please don't use that as an announcement to talk to your manager and say, well, let's buy a machine. It has 4 kilobytes of L1 cache. Okay? The cache line size is 64 bytes. So that happens to be that everything that is aligned to 4 kilobytes is subject to conflicts. Because at the end of the day, when you touch the next 4 kilobytes, you need to swipe out the whole first level cache. Okay? Same for the second level cache. If the data, everything is apart 64K, there's a good chance that you get cache conflicts all the time. Okay? And we can get rid of that by turning the associativity of the cache up. But at the end of the day, ultimately, you get problems. Okay? So the only way is whenever you see a high cache miss rate and your references or array dimensions or whatever data structure are a multiple 4K and you get a lot of L1 cache misses, then you got a problem with that alignment. Or if you have 64 kilobytes and see a lot of L2 cache misses, you got a problem on the L2 cache. Okay, and so the idea here is to pad the array dimensions in a way that you get rid of this 4K, 64K alignment properties. Okay, so instead of having a 16-element array, do a 17-element array and get rid of a couple of array elements during computation, but that would shift all your data. Okay? At the same time, 4K transfers in terms of DMA are the fastest. Okay? So you should make sure that your data starts as a 4K boundary, okay? But all the dimensions are a little off in terms of the page boundaries. Okay? So there's, again, a certain trade-off between getting fast transfers to and from the coprocessor and getting problems in the cache. Okay, so it's a little bit of fine-tuning in terms of sizes and so forth to do that. And the best way to have really odd numbers is to have the array dimensions being prime numbers. Because then they cannot accidentally divide by something else and provide 4K as a dimension or something. Okay, so what happens is the following. You got main memory. And the cache line size is 64 byte. Okay? So what happens is that the main memory is basically divided in 64 byte chunks. And those chunks are assigned to cache lines. Okay? And or into a set in the cache if it's associative. Okay? And now the same cache line always goes into the same location or in the same set. And then there's some other cache lines 4K apart that goes into the same slot. And it's basically we shift 4K through the main memory. And associativity helps a bit, but still you get conflicts on the same cache set. Okay? And now if you can break your data structure in a way that the data that you're loading in this cache line is a little off, then it will slip into a different cache line. Okay, and then you're done. That's the idea behind that. And of course the same for 64 kilobytes. Okay, aligning data for vectorization. So the first element in your array should be aligned to make use of vectorization. And there are basically two ways. If you get static memory that is allocated by the compiler or by the linker, there's an attribute aligned n, where n is the alignment property that you want. So for example, 16, 32, 64 bytes. Okay, so you can make sure that the compiler takes care to align that particular array, variable, structure, or whatever at the corresponding address. Okay? Same, by the way, for stack variables. If you get something on the stack, it is typically aligned 16 bytes, but sometimes you need to align it to 32 bytes or 64 bytes. And if you want to do alignment on dynamic memory, there are basically two ways. The first one is mmap, which takes a second argument alignment bytes. There's a little syntax error here, but don't worry. So for example, you would use malloc on a certain buffer size with 4K, and it would make sure that the malloc happens at the 4K boundary. Okay? And you, of course, need to use a special free function. The other way you can do it is POSIX memoline. That's kind of the standard POSIX way of doing it. This is an intrinsics of some of the compilers, so ICC and GCC and Microsoft. Okay? And most other compilers that are compatible to Microsoft and GCC. So PGI should also support that, for example. Okay. Yes, and the other thing is gather scatter. We had a couple of chats in the coffee break around irregular grid structures and gather and scatter operations. So what really kills performance is that. Okay, that essentially means you can load that as a vector, but since this is an index array, it might, contain different memory locations. And so if you want to vectorize that, you basically need to load every single element from main memory and put it in a register. Okay, that's expensive. We can do that. Performance is on the low side usually, okay, because you get, well, one memory access per element in this vector. But at least it vectorizes. So if the loop here is big enough, you might get a performance benefit. If it's a tight loop, as we have it here, the overhead of gather and scatter might be too much to compensate with vectorization. Okay, so the only thing that you can do probably either find another algorithm that doesn't use the index structure. So sometimes we've seen examples where the data structure was using this index array, but ultimately the operation that was implemented just went through the data structure in a very weird way, and you could rewrite the algorithm into a sequential loop that just went through and did the same thing. This is not possible in most cases. The other thing that you can do is you can convert arrays of structures into a structure of arrays. So let's say you got a picture image analysis program and you want to work on RGBA values. Okay, typically you would have a C++ object or a C struct that contains red, green, and blue. Okay, and then you would have an array, a two-dimensional array of those structs, and that's your image. Okay, and now typically you process the red values at the same time, the green values and the blue values at the same time with the same operations, but not across the colors. So you wouldn't do the same operation with red and green, for example. So the way how to handle that is to create an array of reds, an array of greens, and an array of blues. Okay, so the first one I described was arrays of structures. So we had an array of individual structures, and now we have a single structure that only contains a couple of arrays. And now you can process all the reds in one go, all the greens, and all the blues. Okay? And you either need to keep the data structure, or we also had some successes in converting, running the kernel, and then converting it back. Okay? Okay, that's about it. Yeah, you already heard that. So we have offload explicit and implicit. It's cool, it works well, it's nice, it delivers performance. However, if you want to optimize for K and C, you need to do a couple of things. But the nice thing is the optimization techniques applied are from the traditional Xeon world. Okay, so whenever you optimize your code to run better on mic, it will very likely also benefit on Xeon and will exploit additional performance. And I had one very good statement at International Supercomputing. There was a guy from, I forgot which company, but he said, the great thing about mic is, or Xeon Phi, is to get easy to a good level of performance. Much easier than with GPU, so I'm just quoting, I'm not talking Intel here. So it's really easy to get a good level of performance, but when you go for maximum performance, it's getting equally hard on Xeon, Phi, and on a GPU. Okay, but the great thing is, all those techniques I've showed are rather easy to implement in a real code, and they already push you to a good level of performance quite easily. Okay, I think that's about it.